Hi there! Let me show you a basic example to clear how the solution method looks like for determining the reaction forces. A beam is connected to a roller support in A and to a pin joint in B. Two forces act on the beam. F1 is 100 newtons, F2 is 50 newtons. F1 acts in the middle of the beam and F2 acts in point A. So the loading and the geometry is well known. We need to determine the reaction forces in A and B. First of all, we should always draw a free body diagram. The first step is to choose a coordinate system. Now I choose to work in the xy plane, where x points rightwards and y points upwards. The loads F1 and F2 can be copied from the problem sheet, and then we should put the reaction forces on the free body diagram. In the pin joint, the displacement is constrained in both directions, so there can be a Bx force component in the x direction and a By force component in the y direction. The orientation of the vectors is up to me. Depending on the reality, I will get a positive or a negative result. The roller support only constrains the displacement perpendicular to itself, now in the y direction, so there can only be an Ay component of the reaction force in A. One way to solve the problem is through writing up the equilibrium equations. There is equilibrium, so the sum of the forces is zero and the resultant couple of the system of loads is zero in any point. So let's start writing up equations. In 2D we will have three of them. The sum of the forces is zero in direction x. In direction x there is Bx and F2 both with positive orientation. So Bx plus F2 equals to 0. The sum of the forces is also 0 in the direction y. In that direction, Ay and By are pointing in the positive direction and F1 points in the negative direction. So Ay plus By minus F1 equals to 0. The resultant concentrated couple can be written up to any point, as you have learned in the lecture about reduction of loads. I choose point A. So the sum of the concentrated couples and the moments with respect to point A is 0. There is no concentrated couple, so we only have to deal with the moments of the forces. Ay, Bx and F2 are going through point A, so the arms of these forces are 0. Only By and F1 have moments with respect to point A. The positive z direction is pointing outwards of the plane. Place your thumb in the direction of x, so to the right. Place your forefinger in the direction of y, so upwards. Straighten your middle finger to the third direction. It points towards yourself, outwards of the plane. If positive z is pointing in that direction, the positive direction of the moment can be determined by adjusting your thumb in that direction. So point your thumb towards yourself. Then your other fingers show which way is the positive moment and rotation. Now it is counterclockwise on the xy plane. So By times L is a positive moment with respect to A, and F1 times L over 2 is a negative moment. Now we have the equations, we just have to solve them. In this case it is quite simple. From the first equation we get Bx. Bx equals to minus F2, so it is minus 50 newtons. From the third equation we can determine By. By equals to F1 over 2, so it is 50 newtons. From the second equation we can determine Ay. It equals to F1 minus By, so it is also 50 newtons. The results can be written in vector format. Now you should write the vector components in the global coordinate system. This would be important if I said that Ay, for example, points downwards. Then I would have got Ay equals to minus 50 as the result, but the a vector would be equal to 0 in x and minus ay in the y direction. So minus 50 would be 50 again. A graphical solution can also be done. A graphical solution always requires scale. I choose 10 newtons to be 1 centimeter. This solution method is based on the equilibrium of 3 forces, so you cannot do it if there is a concentrated couple. You can see way more forces on the Freebody diagram, but there is always 3 forces. Now one force is in A, one force is in B, and 2 forces acting on the beam, but the resultant of these forces can be determined, so only one force remains in the problem. To graphically get the resultant, you have to search for the intersection of the lines of action of the 2 forces. In that point, the forces can be added according to the parallelogram law of addition. Finally, we only have one force, F12, as a load. The next step is to solve the equilibrium for 3 forces. 3 forces can only be in equilibrium if they are in one plane, which is surely true now. They must have a common intersection point of their lines of action. This is what we have to ensure now. We know F12 and we know the line of action of A. It is perpendicular to the roller support, so it must be vertical. The 2 known line of actions are crossing each other. At the beginning, I had no idea about the line of action of B, but now I know that it must go through that intersection point, and of course it goes through B because it acts there. So I can draw the line of action of B too. The forces must form a closed vector triangle, so I copy F12 to the intersection point and I draw a line parallel to the line of action of B to the end of the new F12 vector. Now the closed vector triangle is forming, but it is also important that the directions of the vectors must be connected continuously. Now we got the result. With the help of the scale, we can get numerical results. Believe me, it is the same as the ones that we got with the calculations. Thank you for your attention. If you like this lecture, you can check out my statics course for more. You can find a link in the description with which you can buy my course with a discount.